So in this lesson, we're going to be talking about wave properties and learning tutorials to be able to describe the types of waves and the properties of waves. So first, we've got to make sure we know what a wave is. So a wave is a disturbance that transfers energy from one place to another without transferring matter. And this is an important part that we sometimes forget really easily, is that the waves don't transfer matter, they only transfer energy. So if this wave was moving, and we'll see some oscillating waves as you get going, but if this wave was moving in this direction, like say this crest was moving here, this crest was moving here, you guys have seen a wave move before. This red dot right here would only be moving up and down, up and down, up and down. It wouldn't be transferring along here, right, with the wave. The wave would only be transferring energy. And the energy is being transferred because this red dot is moving up and down. Potential energy is going up and then going back down and up and down and up and down, but it's not changing anywhere. And so um, that's an important part that's going to come over and over, is that waves transfer energy, but they do not transfer matter. So the stuff is not moving from place to place. And so how do waves transfer energy? Well, waves transfer energy a lot of times by vibration, but they have to have some sort of energy coming in. If you think about if somebody was going to jump into a pool, we know that if they jump into the pool, there's going to be some waves coming off. And this guy here has quite a bit of potential energy. And when he falls down, he's going to be transferring that energy to the pool, right? And then from here, waves are going to move outward in this direction. His energy that he transferred to the pool from his potential energy going down when he hit that thing is going to be moving. And then if those waves traveled out and they hit these guys that are laying on these little raft things, they're going to move up and then they're going to move down from that wave coming through. So some of his energy is going to be transferred to these guys from these waves that are traveling out through there. So it all starts with some source of energy. A lot of times it comes through a vibration, which we'll see a little bit later. But there's two different types of waves we're going to be talking about. And one that you need to know is called a transverse wave. And this is a wave in which the disturbance is perpendicular to the direction the wave travels. If this guy is going to shake this rope up and down, this wave is going to be moving in this direction. It's going to move towards the tree. But the disturbance from this, if we think about where this rope would be if he was just pulling it tight, the rope would actually be along this line right here. Right now, the wave is going to travel here, but the disturbance, the way the rope changed, is up and down. My disturbance is up. It's basically like how did it change relative to where it would have been anyways? And so because the wave is traveling in this direction, but its disturbance is up and down, that's called perpendicular. And so that's called a transverse wave, one that looks like this. It's going up and down and up and down. It has 2 points that we need to know. One is called the crest, up the top, the very high most point, let's say highest point. And it's also got something called the trough, which is the lowest point. If you need to remember these, you can think of the crest of a hill as the top point, and the trough is like a place where, I don't know, like horses and cows drink out of. It's kind of got a low bottom where water will sit down there. But we've got a crest and trough on our transverse wave. So the second type of wave is called a longitudinal wave, and this is also called a compression wave, where particles are compressing close together and then springing apart. And this is a wave in which the particles in a medium move parallel to the direction that the wave travels. And if you don't know what this word medium means, in this case, we're going to use it to describe the material, the stuff that this wave is moving through. So in this case, we have this slinky. You've seen this before. If we pushed all the parts of the slinky together, the little coils, we'd have something called a compression. Right? This is another part that you need to remember, the two parts of longitudinal wave. We'd have a compression where all of those slinky coils are going to be compressing together, and then they're going to spring back out, and all the way over here, until they compress together again. And then they spring back out. And the wave is still going to be moving along in this direction. You're going to be able to see this compression is going to move all the way over here. And so you can see that my disturbance and the way that my wave is moving are both in the same direction. And so they are parallel to each other. And this is called a longitudinal wave. And it'll look like this. And like I said, there's two parts that we need to know. They're called a compression, the parts where they're very tight together, or compressed. And then rarefactions. This is kind of a tricky word, so if you need to write it down, make sure that you do that. Our rarefactions is where they're spread apart. Essentially the opposite of our compressions, but that's a longitudinal wave when the disturbances move parallel to the direction the wave travels. So we've got three different properties of waves that we're going to be looking at. These are going to help us to identify the energy of the wave and really describe the differences of waves from each other. And they're going to be frequency, wavelength, and amplitude. You get a little bit of a sampling here. You can see that high frequency, what a wave like that looks like. Right here, we have our low frequency, and you can see what a wave like that looks like. We can see our long wavelength here and our short wavelength here. You can see the distance between crest to crest and crest to crest. And then we can see what our amplitude looks like here. It's that distance right there. We're going to get into them a little bit more in depth right now. So our frequency is actually the number of wavelengths that pass by a point each second. If I have a certain point that I'm going to mark, kind of like a finish line, remember these waves are moving in this direction. And so high frequency means that there's a lot of waves moving past this point every second. Again, they're bunched up really tight. You can see what's going on here. And if they're moving past, there's going to be a lot of those wavelengths passing this point, as opposed to this one, where if I have my same point and these waves are moving at the same speed, I'm not going to have very many waves moving past this point every second. And so this is considered a low frequency wavelength, and this is considered a high frequency wavelength. And this is going to be measured in hertz. That's essentially how many waves move every second. And then you might see this every once in a while, S minus 1. It's essentially saying how many waves per second. And we can show dividing by a second is S to the negative first. And one thing that you're going to see is that vibrations cause waves, again, as a source of energy. And so one vibration equals one wave. This is essentially how many vibrations are happening per second. And so for our wavelength, this is the distance between from one point on a wave to the same point on the next wave. If I was going to be looking at this wave, I would go from crest to crest, and this would be my wavelength, the distance there. Or I might go trough to trough. This might be my wavelength here, the same point on each wave. I can't go from here to there. That's not a full wavelength. See how that's shorter. I could go from here to here. Those are the same points on each wave. Now, a lot of times we won't do that because it can get confusing and sometimes we can get screwed up with what part of the wave we're supposed to be going on. But you can always be assured that peak to peak, trough to trough will work out well for your wavelength. And we can have the same thing here for longitudinal waves. We go from compression to compression. Probably wouldn't want to go from rarefaction to rarefaction, a little bit tougher there, but we go from the middle of a compression, the middle of a compression, and that would be our wavelength. And again, our wavelength is measured in some sort of distance. So it could be meters, it could be nanometers, it could be micrometers, it could be picometers, it could be kilometers. But we're going to have our wave measured in some sort of distance, and so that's going to be our wavelength. Just remember, same points. Our amplitude, you can see what our amplitude is here. It's the maximum distance that the wave moves from its rest position. So if this wave, this rope, whatever this is, was at rest and it wasn't having a wave move through it, it would be right at this position. Our amplitude is how far that moves from that position. It could be up, it could be down, it could be up, like you can see there. But our amplitude, you can remember it as how high is this wave from where it would be normally. And because it's a distance, it's how high we can measure that in meters, nanometers, same thing, any of those distance measurements. So those are our three different properties of waves. Remember, the transverse wave is this type like this, where the disturbances move up and the wave moves in this direction, perpendicular to each other. And our longitudinal wave would be something like this, where our disturbances move parallel to the direction the wave's moving. And then remembering our frequency, amplitude, and wavelength.